All right. All right, we can continue the conversation in the break. All right, we got 5 minutes. You guys can catch up in the break, okay? About these nasty kids. So everyone got the homework?
Yes.
Can everyone confirm that?
No, I do.
Is it on the Google Drive? Oh.
No.
Right.
I just printed it out for everyone.
Now I got it.
Now it's on the Google Drive.
So
What is it? What's the thing he has for our class? Is it a Google Drive?
there's one.
Dropbox is what it's called.
Yeah. There's one more, right? It's
Yeah, Dana.
it's you can pass it on to her. Yeah. That would be great. So, homework. You guys know what that means?
Oh, yeah.
Test, homework. So I put the due date is about a week from now. That will be the due date for second chapter or chapter 7 in the book. We're gonna go through it. Okay. I purposely left some of the question a little bit open, so you guys need to do a little bit of research on your side, but it won't be too much. Please get it down for Tuesday class. Thursday class. A week from now, okay, the due date. And the test, I'm thinking about 2 weeks from this week, okay? 2 weeks from today. So what's gonna happen is, like previously, we're gonna go through the homeworks due a week from now. Then, the Tuesday after the homework due, we're gonna go through the homeworks, explain all the questions you guys have. Then we're going to have the test the day after that. So I don't have my phone with me, but you can see the date. 2 weeks from now would be
25th?
2 weeks from now. So the 15th.
Okay, yeah.
15th, we're going to have a...
On Thanksgiving.
Yeah.
that will be epic. I'm sure I will receive the worst review for the teaching. For giving the test on the Thanksgiving, right? Okay. So the timing works for everyone, right?
Yeah.
Okay, that's great. What are we gonna do today? What we gonna teach today, and what we gonna do?
Quick question. Is there a final for this class?
Huh?
Is there a final for this class?
Yes, there will be, and it will be closed book, not take home.
Closed book.
Yeah, I will. Dana? Yeah?
Is our next test take home?
Yeah.
Yeah. So let's talk about class. Don't worry too much about test. I looked at the last test. I think most of you did a pretty good job. You know, I don't expect someone will get a D or C for this class, but
I didn't know that was an option.
there is an option.
It is.
And there is even a fail option, but I don't think everybody is anywhere closer to that stage. But I can clearly see someone is more ahead than the other, so they are likely to be A and B. Okay, so if you want to get A, pay attention to the test and homeworks. Get back to the topic. What are we going to teach today? We already teach it about polymer solutions. So how does polymer dissolve and how the phase diagram looks like. And we use the Flory-Huggins to explain a lot. When do you see a phase diagram look like this or that, etc. So in the beginning of this class, I want to explain some of the final things for this phase diagram. So there are generally categorized several phase diagrams for polymer solution. They are called a short name, LCST and UCST. So the concept is these are generally talking about two different phase diagrams. LCST is this called low assist. Actually, I believe it's lower critical so which means there's going to be a critical temperature for your system to go from one phase to the other. And UCST means there's going to be an upper critical so the difference between these two are basically one case look like that, the other will look like. So this is called LCST behavior because there is your material will go from two phase to one phase. Okay, vice versa. Well, this is okay. So that's two of the last concept, UCST and LCST. So it's just a little bit wrap up of what we talked about in the last lecture, where how the phase diagram looks like. So the main dessert or the main entry for today's class is something totally different. We will talk about osmotic pressure and how we can use that to link to the phase diagram and solvent property. So let me take up some of the space and start talking about the concept we're going to talk about today. So today's lecture is about osmotic pressure. So anyone can help me understand what the concept osmotic pressure means? And do you see it in your daily life? How does this? What does this parameter mean?
Pressure behind diffusion or something.
One. Any thing? Dana?
The pressure water creates on a membrane as it's trying to diffuse through.
Yes. So what is this pressure means? If we have, let me draw. If you buy a large fish tank, like Dr. Nance, he has a big fish tank, but he doesn't have a membrane. However, if you make a large membrane in the between, in one side, it's just a pure solvent. On the other side, if you have polymer, dilute, let's call it dilute polymer solution. So it's on the other side. And to show there actually in real there's a couple polymer flying around, I'm going to use the red color, paint a bit. So these are the polymer chain. And they're going to be an osmotic pressure just because your chemical potential for the solvent on two sides are different. And you can think about the case where you wanted the two sides to have, ideal case, you want half of these polymer molecular to migrate to here so that you don't have any chemical potential difference, right? Because the concentration, if you think about the other way, the concentration of or the chemical potential for the solvent molecular are different between two cases. So if this is a permeable membrane, which means you can have solvent going one way, in the end, what will end it up is it will create, again, I'm going to put this membrane here. This is the same thing. However, where you begin with is equal height in the water level or solvent level. At the end of this process, there will be slightly taller on the right-hand side. And the difference in this, the height, is generated by the osmotic pressure. Now, there's still going to be osmotic pressure, but it will be equalized by the pressure generated by excess amount of the height. Okay?
With
So
the pure solvent on the left, because the solvent's going to the right,
right.
that level decrease?
Yes, it will be. So so if we draw the original level, it will be somewhere in between. But with the time, it will equilibrate and form this excess delta P, because you have a bit more solvent there. That generate the pressure difference on this side and equilibrate the difference. And I still need to put our tiny polymers here, because otherwise, if you take away all the polymers, it doesn't work this way, because then the solvent will come back, right? So these are Nathan? Any? Okay. Is there anything? Anybody have a question about the observation of this osmotic pressure problem?
What's the difference between this and hydrostatic pressure?
Hydrostatic pressure is just that if you stick a sensor to somewhere, there's going to be a pressure you can measure inside it. This is generated by the weight of your liquid, right? So, for example, if you love diving, there's a diver symptom, because you need inhale a lot of. How can I say that? Because you inhale a lot of oxygen while you get out, your oxygen concentration in your blood will change rapidly, because of that pressure generated by water. Or if you go to swimming pool, if you dive down, you will also feel the same way. This is different. This is just talk about the pressure generated on this membrane due to this different internal concentration. Okay, so in this, you got 0 C polymer, concentration of polymer is 0. On the other side, C concentration. Let me write it down. So on the right hand, you have C polymer will be, let's call it C0, where you start from. This could be an arbitrary number, like 1 mole per liter or something like that. And this pressure is actually measurable. So there's other cases where you can measure, basically by measure how tall your material is. Instead of use this large equipment, you actually put a very tiny capillary, and you can measure how high the capillary actually raised by reading it. Okay? This is actually a good question, because that's related to how people measure the vacuum at the very early stage of science research. They would put the mercury into a glass pipe. Okay, it will fill then all the way to the bottom. Then they're just gonna flip it and put a container there, and you can see how much the volume being created, or vacuum being created. Similar. It's just some brief introduction what osmotic pressure is, and this is being useful and has been implemented in many areas. So I'll talk a little bit of application. Everybody heard about what is reverse osmosis membrane. Or they just short this for RO. So what does this technology?
Water purification.
Water purification, right?
So solute will move through the membrane as opposed to the solvent?
No.
Okay.
So in this case, what happens if you leave it a longer time, what you see is your solvent, or you can think about this is if it's a water solvent, water will go into the phase where your polymer are. So in other words, your polymer will get more and more dilute over time and reaches infinite dilute. Then they will match in the chemical potential, right? However, in the reverse osmosis, this is a big sin in especially Saudi Arabia or Middle East area, where the water is really very precious. Actually, they have some saying that a gallon of water costs almost the same price as a gallon of oil in the Middle East. Of course, it's going to be a raw oil because it's really scary. It's most of the country is a desert. So what they do is they use RO technology to generate pure water. What they did is a reverse process. So in this process, you can see the solvent is going to go into here. So you always lose some of the pure material with time. So what if RO, which means, let's draw the same diagram. So then let's call it water. This is going to be the seawater. If you have a membrane to separate where only the water can diffuse, molecule can diffuse past it, then this is basically a salt, right, in water. And this is sodium chloride. You can think about that case. So if you can create a membrane that only allows water to pass but not sodium or chloride, then you can generate a membrane. And if you leave it like this without any external influence, with the time the water will diffuse to the seawater. So what they did then is just apply a pressure in this side. So if they put the pressure on the other side, which now you can reverse the process. So that's what they call it, a reverse osmosis. So you now generate pure water from the seawater. That's a fundamental of that. And how much pressure they need to put it at least to be bigger than the osmotic pressure, because otherwise they will not be able to overcome the chemical potential difference. Okay? So some of the background information help you to understand what is osmotic pressure is. So today's lecture is more specific about how about the polymer and what is osmotic pressure you can generate from a polymer. Okay? So in this case, we're going to talk about what is osmotic pressure for, again, I like this drawing. So this, you're going to have the solvent. Again, you're going to have polymer plus solvent, and what will be the osmotic pressure? And this a symbol looks like a pi, but it's probably a capitalized pi means osmotic pressure. Okay? So I want to use the rest of today's two lectures to talk about how do we understand this problem and how can we learn from osmotic pressure experiment for the polymer solution. And why this is important? This will be related to the next next chapter on light scattering and dynamic light scattering. This is also called static light scattering, which I will not teach you guys, but Dr. Yong Simon will talk to you what are these techniques are. This sort of foundation laying, and what also important is it will show you how you can use osmotic pressure to characterize molecular weight. Okay, and also the solvent quality. You can also use the dependence of osmotic pressure on concentration of the material. So in other words, this is useful enough that you can, by looking at how does osmotic pressure changes versus concentration. So usually what you do is prepare different concentration of your polymer. Then you look at what is osmotic pressure differences. And interestingly, I'll give you a little bit overview what we're going to see. So if we plot this osmotic pressure versus concentration, this is concentration of your material, and how would they depend on each other? Any guess? Will they be this way, or this way, or that way? Everybody say 1. We got 1, 2, 3. Anyone think it's 2? We got 3, 1, right? Is it? Am I counting the right person? Whoever thinks it's 1. Oh, it's a majority. So we got 6-ish. How about 2? Anyone think it might be flat?
I feel like, is it flat? Because you're putting such a, it's like a trick question.
No. I just want to get a feeling about you guys. Anyone think it might be flat? No risk taker? How about 3? Cases 3. Anyone think?
Y'all have to vote.
Yeah.
Okay, I'll take a risk. I'll go 2.
Okay.
You said 2.
Is it pressure?
This is osmotic pressure. That's concentrate.
I want to be number 2 here. I think we're on to something.
Does it have to do with, like, is it like a cost equilibrium or something like that?
Well, I want you to think about what the possibility. If you think about you prepare sugar in water or honey in the morning, then you put a different concentration. Do you think the osmotic pressure will change or it will stay the same?
Oh, it stays the same.
There we go. Hey,
So-
I'm kind of feeling like it's the same.
Okay, there's no one takes number?
Solve it, damn it.
No one takes 1, 3? No? Okay. Where are the other 2? Whoever didn't vote. Okay. All right.
1 and 2.
Is diffusion speed the same, or is it directly proportional to osmotic pressure?
So that's a good question. We haven't talked about the speed because think about this. The speed is not directly related to the pressure. It will relate to the pressure difference, but also relate to the membrane property. It's going to be thick or not thick. So it's a kinetic problem, but we only going to teach you guys about thermodynamic. So you can think about it's cooked for long enough time, almost infinity, and what the equilibrium state will be look like. Okay. All right. So I'll put the rest of the 2 people here because they didn't vote. It's a good voting rate, right? Its turnaround is more than 70%. You know, in the U.S., I heard the voting rate is only maybe 40–45%. So only half people would vote. Yeah. So we will find out whoever is right. And remember your vote, okay?
I would prefer 2 if it's right.
Okay. So that's what we're going to do. And we will figure out which one is right today and why it is correct. So now, let's actually dive in a little bit physics about what is osmotic pressure and what is dependent on. So we're going to go back to, again, to a very abstract term called chemical potential, which is, this is written as mu1. And 0 means there's just a solvent only, okay? So on the left, and typically they would put a bracket and put the temperature P and T, which means it's considered at a constant pressure or temperature or at just the same temperature as the other case. And you will see it will depend on the difference between the other is, in this case, we will write as mu1 as P and T, and plus they're going to be osmotic pressure plus volume, molar volume of your material, or V1. So that's just an average of materials property, okay? So this is a very generalized equation, but it's giving you the hint how does the osmotic pressure would influence chemical potential. And in the previous class, we know the chemical potential of your material is first derivative of free energy to the molar volume of your material, right? So if we sort of rearrange this, looks a little bit daunting equation, we're going to have V1 going to be equals to and this actually turns out to be fairly straightforward. So that would be the volume fraction of your, let me make sure. So this would be the volume fraction of your polymer. oh sorry, solvent, because we are looking at solvent chemical potential. So the X1 is molar volume of solvent, because what we're talking about here is chemical potential for the solvent will be equal on the left-hand side versus on the right-hand side. That's the equilibrium condition for the membrane. Okay, so at the membrane position, you're going to have pressure coming from the solvent. You're going to have pressure coming from the polymer plus this pressure. They will be equal. Okay, and they just equal right here. So there is no movement for the solvent. What do we do next? So what we know is usually osmotic pressure talks about relative dilute solution. So in this case, which means your X1 or molar volume of the solvent X1 will be close to 1. Okay? Or think about the typical case if you have 1% of the polymer, which means you're going to have X1 equals to 0.99 because that's molar volume of the solvent. So you have a lot of solvent there. We can consider now, instead of consider osmotic pressure of the solvent case, we can rearrange this in terms of polymer. So X2 so that's a polymer. When you add them together, they're both going to be equal to 1. Okay? How does this can be further simplified or complicated? And this can be understood by, again, this is using a very familiar process called Taylor expansion. We talked about in the early stage of the first chapter how does expansion for this works out. If x1, x2 is much smaller than 1, your ln 1 minus x2 going to be equals to minus x2 minus 2 over x2 squared minus 3 . So this is not something we invented. This existed a long time in history. So in other words, what we will get in this will be x2, right? So if we expand this, use this equation.
Is that a natural log?
Yeah. ln and I'm missing minus RT here because you're still going to have minus RT at the front of. Okay, so we are pretty close to what we want to achieve. Is basically if we rearrange a bit, we will get this. If we move this to the left side, we will get pi divided by RT will be equals to x2 divided by V1. So this is a molar volume plus, let's call it a constant, okay? So what does this means is we now start to see how would the osmotic pressure relate to the polymer concentration. X2 is molar volume of your solvent. Molar volume of, where did I write? Molar volume of your polymer, or how much polymer you had in there. So if you look at this, you will see pi, or osmotic pressure, divided by RT. Again, these are at the fixed temperature, it's a constant. Or you can think about the unit of energy, okay? Equals to X2 divided by V1. V1 is molar volume. You can think about this is how big a solvent molecular its size is. And this would be a constant as well. So X2 is molar volume of the polymer. And if you know what does this mean, you know, molar volume can be translated to concentration. If you know the molar volume inside the solvent, you know, 1 mole out of 100, then you can translate it to the concentration. Plus this term, this is a constant, proportional to concentration of square. So it's also dependent on the or molar volume or concentration, but it depends on the power of the concentration, power of 2, and you will have a certain constant. It will depend on the concentration power of 3 times. So pi, or osmotic pressure, will has some rather complicated. In this, at the first glance, looks like it's quite a complicated. However, if you look at what is, how do you link the X2 and C concentration? So this is a molar volume. Again, like we wrote here, C is a concentration. We can write as C2, or generally C is concentration. Of the polymer. I mean, this is not too hard. It's not rocket science. How does X2 and C2 ring? Dana?
What's X3?
Good call. I owe you a bonus point. It's actually X2. There's no X3. Good call. I was probably writing too fast on the 3. Nice catch. So X2 and C2. C is a concentration. X is a volume ratio. So what links them is basically the molar volume, or molecular weight. Okay, so the molecular weight per volume, you can link them to. So I'll show you how they would make sense to everyone. So concentration would be equals to weight, right, divided by volume. So if we know you got X2 mole solvent, so you can basically write as N2. N2 is how many mole of solvent there. Multiply by molecular weight of your polymer. This is the unit for this is, this would be gram per mole. So this would be the mole, right? How many moles of your solvent you have, divided by volume. So this would give you the concentration of your polymer. N2 multiplied by M, that's molecular weight, okay? That's V. Let me write this for you. So what I'm trying to do here is basically correlate this X2 to concentration. so that I will explain to you guys how does pi and the C correlates. Because and now we only know the relative relationship between pi and the molar volume, right? So how does it work out? If we plug in the equation we had in this case, where we know what is x2, right? So let me show you guys what is x2. Use some space here. So x2 is the molar volume of polymer that equals to N2 divided by N1 plus N2. So this is a mole of solvent. This is a mole of polymer. So that's a definition of what is molar ratio. So using this, what you can get is this is going to be equals to CV divided by N. It's going to be V. So V1 is what is the molar volume for the solvent? Okay. So can someone let me know if you have a question on this particular equation? So x2 is molar volume of your solvent. You will divide by, let's say, example of this would be if you have 1 mole of polymer in 100 mole of solvent. So x2 would be equal to 1 divided by 1 plus 100, right? And what we're doing here is now convert that to the concentration using this one. So we know N2, based on this equation, you can see N2 going to be equal to C multiplied by V divided by N. Concentration, volume of your material divided by molecular weight. It's not that bad. So now the question is, how do we understand this? As long as we resolve what is x2, we can plot pi or osmotic pressure directed with concentration on your material, which is x2. So if you take a look at this equation, if this can be approximated to be concentration divided by N. This is molar volume of your material. This can be take approximation if N1 is much bigger than N2, which is usually the case for the dilute solution. As you can see, 1 divided by, in this case, 101 is roughly equals to 1 divided by 100, right? So if we do the same approximation, omit this one term, which is N2 here, which is omit this term, this CV divided by N is equal to C divided by N. And this in the bottom going to flip up to the top. That is molar volume of your system. Okay? So we now established the connection between the concentration of your polymer versus the molar volume of your polymer. X2 equals to B1C divided by N. What are we going to do next? Anyone can help me? What are we going to do next?
See which one's right.
We're very close.
Like
But
to make the change the formula to make it to what else are we doing to that thing? Is that what you're asking?
yes, I think it would be useful. We just put this. So this is the connection we can plug into what is x2 is. So if you do this, so if we know x2 is equals to molar volume concentration divided by n, we can easily convert this equation pi divided by RT let's call it constant x2 square plus so what would be the first term? It will be this cancels out each other, right? So you would get C divided by N. So what you see is this is concentration, this is M, plus we can rewrite and define this to be a constant, a new constant. Let me first rewrite everything so you don't miss out any parameter. So C divided by N square. We don't need to worry about this term because it's too much. You will still have this. Right? So if we define something new, what we will see is now we can just forget about this very complicated parameter. We define a new term called second coefficient. Secondary coefficient here, if we just call it as B2 equals to this very lengthy term, then we can get this pi RT will be C divided by M plus BC squared. Right?
Does that say virial?
Yes. VIRAL. It's called a very interesting parameter called secondary coefficient. And it's not straightforward to understand what the meaning by reading the character, but physically it has very important applications for what is B or B2, or depending on where you read it, it can be different. Okay, so can we answer this now?
We are all wrong. It's not linear.
It's not. How about this? Let's put it this way.
It's a squiggle.
Oh, there we go.
So now
Okay.
pi divided C plot over C.
In that case, then it would be 1.
Yeah.
What depends on B, right?
It depends on the B. So what Rebecca says, it will depend on what the parameter B is. So if we rewrite it a little bit, pi R divided by C concentration RT, then it will be equals to N. because the concentration cancels out, plus BC. B is second very coefficient. C is concentration. Okay. And why we do this equation? This would be the equation you need to know. And why we need to do this is it is now could be plotted linearly or not linearly, right? So if for a given polymer, the molecular weight should be a constant, right? If you have a polymer and would not change if you add more polymers into the solvent. So this will be a constant. And B is another constant. B is just a constant called second-order coefficient. So it's basically, you can think about this is a linear curve. This is A plus B is another C. Or if you write it as basically on the left axis, it will be y equals A plus bx. So the intercept, if we plot this way, the intercept to concentration at 0, which is 1 over molecular weight, right? And the slope of these three cases are B, right? There's B. So there are 3 B's. And who is right in this case? Is the majority wins, or the middle case, or the last one?
We're all winners.
I think everybody has a possibility, right? Because depending on what the B is, you can have three different scenarios.
All right.
So when would you have the case 1?
What's wrong? Sorry.
Whenever
So
B is positive.
Whenever B is positive. Case 2, whenever B is 0, and whenever B is negative, right?
So that would be dependent on the beta constant, which what exactly determines the beta constant?
That's a very good question. So we're going to resume after we take a short break and discuss what are these specifically 3 cases are. And B actually is a very good parameter, can tell you a lot of things about how does polymer and solvent interact. Okay?
Is a temperature dependent parameter. Also, are you graphing pi over C versus C?
Yeah,
RT.
it has to be pi over C. RT is a constant.
Is that conversion or concentration?
Concentration. It's a C.
I thought you said concentration was constant.
No. Molecular weight is constant. Concentration is changing. If you look at this curve,
Yes,
Yeah.
pi divided C RT, this you need to measure. What you did, for example, if I am the one doing this experiment, I would make 5 concentration polymer. 1 milligram per mil, 2 milligram per mil, 3 milligram per mil, 4, 5. Then I measure. This is physical measurable, what's the pressure they are. So I can measure it to see what's the value. Now where I plot, you need to use pressure divided by concentration as y-axis. Plot with horizontal is concentration.
Okay.
All right?
Yeah, it seems weird, but
Yes.
So
So
if you
Take your word for it.
my whole life.
0, 1. So it's a happy ending for everyone.
No, that was best case scenario.
Huh?
well, except
You're
for
only
2
wrong
people.
if you didn't vote.
Uh-huh.
Yeah, 2 people were wrong.
This is a good lesson, right?
Or were they
before
right
elections.
because they didn't pick one?
Ah.
Yeah, maybe they knew.
The y-intercept is 1 divided by number average molecular weight, or
That is number average molecular weight. So we can talk about why it's number averaged. So
Yeah. I don't have the big thing, whatever that is.
I think HDMI.
Hey, homie, I put in a couple more things.
Nice.
Do you want to come back? Yeah.
Excuse me.
I added these four because it's like what they did was they were trying out different shindigs, and you want like a linear relationship. Yeah. And so then it just shows like the bottom two.
Oh, sorry, hydride. What would be the accurate?
Yeah. It's 29. Yeah. They were
Oh,
linear
Polar
relationships.
Okay.
Yeah.
Yeah. Dr. Gu, so what was Maxwell's costume?
he had a lobster costume.
A
He was a
lobster?
lobster?
So
Oh,
you
yeah?
won.
Yeah,
That's good.
he indeed is.
That's cute.
Will you show us pictures after class?
Yeah, that's not a problem. I don't see why that could be a problem. Okay, so let's slowly get back to the pace. What we need to talk about is now what the heck is this B and why it shows this kind of phenomena and what we should be prepared for, what the B is and what's the physical meaning of that. So someone asked me how actually those experiments were done. And one of the homework is actually related to that. That's homework number 3. If you look at the homework list, it basically shows you the example, what is the concentration and osmotic pressure of your material. Okay, so that's a very related experiment what you would do. Let's say I am the second year graduate student might ask me to understand if the polymer and the solvent, are they good solvent for your polymer or are they bad solvent or are they non-solvent? And how do you do that? And osmotic pressure is actually a very relatively okay way to determine. How do you realize that? Is first you measure, you prepare 5 different concentrations of your material, like shown in the homework, where you make 1 milligram, 3 milligram, 5 milligram, 10 milligram solution. You weight your polymer, you add your solvent, you dissolve them overnight, so you get 5 bottles. Then you go to a setup, which imaginary it exists. You add your material, then you measure the osmotic pressure for your material. And there's such a equipment that actually exists that you can measure that. So what you will see is now you have one concentration, one pressure, osmotic pressure related to that. You can do it multiple times. And that's what the homework 3 is about. You got 4 to 5 concentration, 4 to 5 osmotic pressure. So what you're going to do next is you're going to divide this pi divided by osmotic pressure divided by concentration. That will be your y-axis. Okay, so this is your y value. This would be a parameter you want to get. What's the molecular weight of your material? In principle, you can get the molecular weight of your material by doing the experiment I described. This is a concentration. So what you can do is now you have known concentration you prepare, and you know what is y value, what is x value, right? So you can generate a plot look like this. This is going to be the concentration C. You got 5 data points. You're going to have, this is divided by RT. These are the constant at a fixed temperature. So let's say you got 5 value as well. Okay, so you can plot them out. Look like this, for example. Okay, this is just an example. Then you can do a linear fitting. Then that will be 1 over your molecular weight. And slope of this would be the B. Right? Everyone got this? Now coming back to what this B is, it's called a second virial coefficient. And this coefficient is some sort of a very easy to understand interaction parameter between your polymer and solvent. And in this case, we show there are 3 cases, right? Where you're going to have case, case B is larger than 0, and case B is equal than 0, and case B is smaller than 0. They actually represent 3 important states of your polymer solution. So in the first case, which means your polymer is a good solvent. In this case, if you increase your concentration, your osmotic pressure divided by C is going to be increased. In B smaller than 0, this means your polymer is in actually bad solvent. So in this case, your osmotic pressure, the more you add in, it can be actually dropped. So how about the middle one? It's a special condition called Zeta solvent. And can someone remind me what is the definition of this Zeta solvent?
Acts like a free joint chain.
Yeah, so it acts as free joint chain. So, good one, good call. So this is how you can relatively easy to understand if your material system is good Zeta or bad solvent. But in real data, one of the tricky things is you would never get something in super flat B equal to 0. So if it's within a certain range, you can see it's almost like a Zeta solvent, right? So, for example, you have this is so close, the slope is 10 to the minus 6, something like that. It will be almost a Zeta solvent, right? So, okay. So that's a very important parameter for the B, and B is direct indication of your solvent quality. And did we also mention in the last class that chi is, or Flory-Huggins is also a parameter such like that. Is also an indication for solvent quality. Right? So if this is also an indication of if your solvent is favorable intact with your material or non-favorable intact, then there are potential some linkage between these two. They might be nephews or siblings, but many generations away. They don't even know they share some of the blood together. But they are, because they describe the same physical parameter if your polymer solvent interacts favorably or non-favorably. So B larger than 1 means they interact favorably. B minus 1 means they interact unfavorably. And how about chi? And we're coming back to this again, a very interesting question about Flory-Huggins parameter. Where in the at the end of last lecture, we talked about how you can use solubility parameter to understand what the chi is. So if you have two material has relatively close solubility parameter, your chi will be smaller, right? So I want to use the rest of 20 minutes to help you understand how does this chi relate to the B, and when does the solvent become a bad solvent at what value of chi. Okay, so for example, if I tell you chi equals to 1 or 100 or minus 100, what's the physical meaning for the chi? We knew about B is relatively straightforward. B larger than 0, good solvent. Smaller than 0, bad solvent. How about chi? We haven't really discussed it much. When does the chi indicate the solvent quality, right? So we're going to handle that as well. Okay, so where can we start?
Our equations for B and chi.
There are linked equations, and that's where we are heading towards too. And I'm curious where we should start from to establish the potential relationship between R and chi. So where is chi is, please?
We have RT in that equation, and we have equations of chi and RT. So can we set those parameters equal to each other, or get the equations to?
Chi is not directly related to RT.
So we have delta H over RT.
Right. That is not directly related. However, there you talked about a very important is Flory-Huggins theory, which links free energy and entropy and enthalpy, right? That's the whole purpose of this course is we covered Flory-Huggins theory. So I'll talk about here. This is an equation you probably saw more than 100 times. I hope you still feel excited to see it again now. All right. Maybe almost 100 times, right? So we got the chi right here. That's a Flory-Huggins theory about just mixing two of the material, not even talking about polymer. Well, we know osmotic pressure going to be equals to chemical potential difference in the solvent plus polymer plus solvent. Okay, this is solvent, right? This is a polymer plus solvent. And that's actually directly related to the partial derivative between the chemical potential, okay, at the constant of P, T, and N2. And N1 is a solvent. So we take molar derivative of free energy, will give you chemical potential for the solvent. And that's how we kind of linked two problems together. How does the Flory-Huggins theory can get us, know the long separated brothers between B and chi. And I know it's late in the afternoon, and everyone is a little bit sleepy, and talking about derivative is probably going to be tough. All right, so I'll do it on the board, but I'll try to explain it slightly and try to omit some of the complicated steps. So the first thing is we need to know what is this.
What is the molar derivative of free energy?
2n1. So you're going to derive this to n1. We did it. We actually did it before, so we don't need to go through it one more time. Yeah. So why don't I help you guys? You don't need to go through. Okay, I'm gonna share those information with you guys.
Is this per system or lattice site?
So this will be the per system, because we are talking about the energy of the whole system. It's not the lattice side because osmotic pressure is more like a collective behavior than a lattice behavior or individual behavior.
Is that a negative sign?
Yes, it's a negative sign. Oh. So this would be the chi. It's a little bit long.
Just a skosh.
But not too bad, huh?
Can you not cancel your phi's right there? Is there
Yeah, we can. We can. We will.
Oh, we're deriving.
We're going in very deep in terms of.
One step in. It's like the only person who was nice to me here is Becca. And Mike.
She's being sarcastic. She's not
You know, we have a horse and a ride home. It's like, God.
You're not gonna get any pay.
All right. Let's focus. Finish this monster in front of you, okay?
Hey guys.
So
Yeah.
it's getting close to the stage where we wanted, right? You can see we almost left with a nice equation, right?
It's not as symmetrical as the one.
Yeah, it's not as pretty as a Flory-Huggins equation, right? But if you do one more step of simplify what is phi r and expand this, use Taylor expansion in one more time. Just one more time, you will see. So this is what you will have. Right? If you do expansion of this, it will become these two terms plus whatever left. Okay, we have two more steps, then we're done. So,
I thought you said one more.
okay. We can fast forward, like watch a movie, huh? So this is what you would relate to. Look at it one more time, what we did between these two. So you have this term is going to be here, right? And this phi 2 canceled out with this phi 2. They are gone. And this minus phi 2 squared divided by 2, and this is chi, which is combine these two to be chi minus 1 divided by 2.
What's the dot dot dot?
Dot 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 is higher order term coming from, yeah.
Yeah.
It's a Taylor expansion.
Okay, I get it. I thought when I was like, I thought you said one more. I thought you were just dotting like.
It's gone.
finishing.
No. I
Figure it out.
How about this? Looks better, huh?
Oh yeah, that's good.
So
is that it? Is that as simplified as it gets?
hmm?
No.
Oh, you
Yeah, it is as simple as it gets, but remember what we wanted to is extra concentration. And here phi 2 is again the volume ratio. So we're going to do the similar equation as we had. And this is going to be molecular weight. Okay, so or you can write it as N V1. So this is a degree of polymerization. So this is a molar volume of solvent. So this V2 is molar volume of polymer. We're pretty close. We did this previously because C multiplied V divided by N will be equal to the molar volume, okay? We're so close, right? So one more step. You will get one last step. If you put in this phi 2 to here, then you can get pi divided by RT will be an equation that you're very familiar with. And there's a c squared. I need to use some of the space here. Did you guys see this equation before?
In the textbook.
No, we just talked about it 10 minutes ago.
Where were you?
Oh, yeah, that's
Most of it, right? So again, if
drop the negative sign? Just kidding.
over there.
so, there is a negative sign right here.
Yeah.
So that would drop right here.
Yeah.
So if I kind of
Move the V.
minus pi but in the essence, what this most important is now, this is very much similar to osmotic pressure we derived coming from what is B2. Right? So if you recall, the other equation says pi divided by RT, and depending on where you put the C, okay? So we can leave the C here or here. If it's here, it's C divided by M plus BC squared. So they look like they could be relatives, right? So B is basically same as this pretty lengthy long term, right? I'll copy that to here. That's correct. So, or you can just use equal term instead of this interchangeable sign. So all these are relatively constant, but this, we talk about importance of B equal to 0, smaller than 0, or larger than 0, determines solvent quality. That can be translated now to this chi parameter. When will the B equal to 0, ladies and gentlemen?
When 2.5.
Or chi is equal to 0.5. That's where your solvent system is very much a Zeta solvent condition. And when does this to be B larger than 0? Chi is less than half. Instantly, good job. So, in the other case, of course, it's going to be larger than 0, right? Larger than 0.5 chi. So that's where your solvent is bad solvent. So now we are getting more clear, or a little bit physical meanings of what the chi are. So if your chi is half, it's Zeta solvent. If the chi, if it's larger than 0.5, then that's a bad solvent. If the chi is very small, then you have a good solvent. It kind of makes sense if you rethink what the definition of the chi. It's from the solubility of A minus B squared. So in other words, if your solubility parameter is close, then the square will be more likely to be less than 0.5. So it will be more like good solvent for two material, right? Yeah. So I think everybody did a wonderful job understand how does osmotic pressure, B and chi, relate to solvent quality. That pretty much summarized this lecture. And so any question for particularly how does second derivative coefficient, what's its physical meaning, and how does it relate to the solvent quality? No? Okay, good, good. I think then we can wrap up this class. So for the next lecture, we already taught most of the solvent quality, solvent mixing, solvent phase diagram. So I want to use one more lecture to summarize the whole chapter 7. Use about 30 minutes to come through what we talked about in the last month. And if there's some more time left, I will start to talk about next chapter. It's going to be a fun chapter. Nothing related to the solvent again. We are jumping back to the chain statistics. But we will talk about a very unique case called rubber elasticity. When does rubber become, why does the rubber has a unique property? Why does it has elastic property? That's actually something that nothing else can replicate its property. Think about the metal coil. I'll give you some introduction. Think about a spring, what you have in, for example, the damper for the car, which has pretty big spring, right? So I'll leave something for you guys to think about. Interesting phenomenon is if you get about 100 pounds students, it's ideal student, anyone, okay? And he has the metal spring on the top of him. Yeah. He held on top of that. That's terrifying. It is, right? I'm getting more funny, huh? This is a rubber. So this is a metal spring. So interesting enough, if they were at the same length at the same weight, if the temperature get warmer, let's say it was a freezing winter at minus 10 Fahrenheit, then you come into Mississippi in the summer, how about 100? Okay. How does this world change? Actually, it's different in two cases. In one case, metal actually going to relax. So in other words, you will have something at high temperature. This is, again, the graduate student is holding it. Then this rubber actually will shrink. It will come back. So rubber case, you will reach somewhere here. And in by the end of the class, I'll explain clearly why they're different.
Not why the grand scales are famous.
Huh? Not hand. I put it while they are grabbing it.
By the end of the class, you'll find the best way to
Okay.
Assuming that
Okay.
It's a good lesson. Thank you.
All right. So.